When addressing conductor size changes, understanding the National Electrical Code Section 240.21 is crucial. These rules govern the installation of tap conductors, which are smaller conductors connected to larger ones. The primary goal is to protect the smaller conductor from overcurrent, ensuring electrical safety and preventing fire hazards. The question at hand involves feeding a pre-made 12-foot by 12-foot by 15-foot enclosure located over 1,000 feet away from the electrical panel. To mitigate voltage drop over this distance, the conductor size needs to be increased. However, at the enclosure, a transition to a smaller conductor, approximately 30 feet long, is required to facilitate connection to the electrical devices within the enclosure. The core question is whether the tap rules outlined in 240.21 must be followed during this conductor size reduction at the enclosure. To answer this, one must understand the fundamental principle of tap rules. Tap rules come into play when a smaller conductor, known as the tap conductor, is connected to a larger conductor, referred to as the main or feeder conductor. These rules are designed to protect the tap conductor from overcurrent conditions, ensuring that it does not exceed its ampacity, which is the maximum current it can safely carry. In the given scenario, the conductor size is being reduced at the enclosure. This means transitioning from a larger conductor to a smaller conductor. The key point here is that tap rules typically do not apply when reducing conductor size in this manner. The rationale behind this is that the larger upstream conductor already provides overcurrent protection for the entire circuit, including the smaller conductor downstream. Therefore, the smaller conductor is inherently protected by the overcurrent protective device, such as a circuit breaker or fuse, installed at the origin of the circuit, which is typically at the electrical panel. However, this does not imply that one can arbitrarily choose any conductor size for the 30-foot section at the enclosure. Several factors must be considered to ensure compliance with the National Electrical Code and to maintain electrical safety. Firstly, the ampacity of the 30-foot conductor must be sufficient to carry the load it will serve within the enclosure. This requires calculating the total current demand of all the electrical devices within the enclosure. The conductor must be sized such that its ampacity is equal to or greater than the calculated load current. Secondly, voltage drop must be considered even for this 30-foot section. While voltage drop is less of a concern over the shorter distance compared to the 1,000-foot run from the panel, it is still crucial to ensure that the voltage of the enclosure remains within acceptable limits. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and premature failure. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Thirdly, proper overcurrent protection must be provided. While tap rules may not apply directly, the overcurrent protective device at the panel must be sized appropriately to protect the entire circuit, including the 30-foot conductor. This means that the overcurrent protective device should not exceed the ampacity of the smallest conductor in the circuit. In this case, it should not exceed the ampacity of the 30-foot conductor. If the overcurrent protective device at the panel is larger than the ampacity of the 30-foot conductor, additional overcurrent protection may be required at the point where the conductor size changes. This can be achieved by installing a fuse or circuit breaker in the junction box at the enclosure. Fourthly, proper grounding and bonding are essential for electrical safety. The grounding conductor must be sized appropriately and connected to all metal enclosures and equipment within the enclosure. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Fifthly, the type of conductor used must be suitable for the environment in which it is installed. If the enclosure is located in a wet or damp location, the conductor must be rated for wet locations. Similarly, if the enclosure is exposed to corrosive substances, the conductor must be resistant to corrosion. When selecting conductors, the insulation type must be considered, referring to National Electrical Code Table 310.16. Insulation types such as THHN, DHHW, and XHHW are commonly used for general-purpose wiring. The selection depends on the operating temperature, moisture conditions, and exposure to chemicals. For example, THHN is suitable for dry locations, while THHW is suitable for wet locations. XHHW offers high heat resistance and is suitable for both wet and dry locations. The ambient temperature in which the conductor is installed also affects its ampacity. National Electrical Code Table 310.16 provides ampacity ratings for conductors at specific temperatures, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds this value, the conductor ampacity must be derated according to National Electrical Code Table 310.15. This derating factor reduces the conductor's allowable current carrying capacity to prevent overheating. The number of current carrying conductors in a raceway or cable also affects the ampacity. When multiple conductors are bundled together, the heat dissipation capability is reduced, leading to increased temperature. National Electrical Code Table 310.15 provides adjustment factors for the number of current carrying conductors. These adjustment factors reduce the conductor ampacity to compensate for the increased heating effect. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity must be reduced 80% of its original value. Voltage drop is another critical factor in conductor sizing, particularly for long runs. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and premature failure. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. The voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance. The resistance of the conductor depends on its material, length, and cross-sectional area. Larger conductors have lower resistance, resulting in lower voltage drop. The formula for calculating voltage drop is volts dropped equals 2 times length times current times resistance per 1000 feet divided by 1000. Where length is the one-way distance in feet, current is the current in amps, and resistance per 1000 feet is obtained from National Electrical Code Chapter 9 Table 8. The National Electrical Code provides specific requirements for conductor identification. Grounded conductors, typically neutral conductors, must be identified by a white or grey color. Ungrounded conductors, typically hot conductors, can be any color other than white, grey, or green. Equipment grounding conductors must be identified by a green color or a green color with one or more yellow stripes. The conductor must be installed in accordance with National Electrical Code Article 300, which covers wiring methods and materials. Article 300 specifies the requirements for raceways, cables, and other wiring methods. Conductors must be protected from physical damage and installed in a neat and workmanlike manner. The National Electrical Code provides guidelines for conductor termination. Conductors must be properly terminated to ensure reliable electrical connection. Terminations must be made using approved connectors and methods. Termination must be tight and secure to prevent overheating and arcing. The National Electrical Code Article 314 covers outlet, device, pull, and junction boxes, conduit bodies, fittings, and handhole enclosures. These enclosures must be sized appropriately to accommodate the conductors and devices installed within them. The enclosures must be accessible for inspection and maintenance. The National Electrical Code Article 408 covers switchboards, switchgear, and panel boards. These electrical distribution systems must be installed in accordance with National Electrical Code requirements. Panel boards must be properly labeled to identify the circuits they serve. Overcurrent protection devices, such as circuit breakers and fuses, must be installed in panel boards to protect the circuits from overcurrent conditions. The National Electrical Code Article 430 covers motors, motor circuits, and controllers. Motors must be protected from overload and short-circuit conditions. Motor circuits must be sized appropriately to handle the motor's starting and running current. Motor controllers must be selected to match the motor's voltage, current, and horsepower rating. The National Electrical Code Article 440 covers air conditioning and refrigerating equipment. This equipment must be installed in accordance with National Electrical Code requirements. Disconnecting means must be provided to isolate the equipment from the electrical supply. Overcurrent protection must be provided to protect the equipment from overcurrent conditions. The National Electrical Code Article 500 through 516 covers hazardous locations. Hazardous locations are areas where flammable gases, vapors, liquids, dust, or fibers may be present. Electrical equipment installed in hazardous locations must be specifically designed and approved for use in those locations. These electrical equipment must be explosion-proof or intrinsically safe to prevent ignition of the hazardous materials. The National Electrical Code Article 547 covers agricultural buildings. Agricultural buildings, such as barns and poultry houses, often have unique electrical requirements. Electrical equipment installed in agricultural buildings must be resistant to corrosion and moisture. Grounding and bonding are particularly important in agricultural buildings to prevent stray voltage. In summary, while tap rules as described in National Electrical Code Section 240.21 may not strictly apply when reducing conductor size of the enclosure, several other National Electrical Code requirements must be considered. These include ampacity voltage drop, overcurrent protection, grounding, bonding, conductor type, ambient temperature, number of conductors, conductor identification, wiring methods, conductor termination, and applicable articles for specific equipment and locations. By carefully considering these factors and adhering to the National Electrical Code, one can ensure safe and code-compliant electrical installation. To reiterate, the tap rules outlined in National Electrical Code 240.21 are generally applicable when a smaller conductor is tapped from a larger conductor. The exceptions listed in 240.21 provide specific conditions under which tap conductors are permitted without requiring overcurrent protection at the tap point. These exceptions are based on factors such as the length of the tap conductor, its ampacity relative to the load it serves, and the overall protection provided by the upstream overcurrent device. However, in the scenario described where the conductor size is reduced at the enclosure after a long run to address voltage drop, these tap rules do not inherently come into play because the primary concern is the reduction in size, not tapping from a larger conductor. The requirements outlined above for ampacity, voltage drop, and overcurrent protection must still be met. The final conductor size chosen should be sufficient to carry the load current, maintain acceptable voltage drop levels, and be protected by an appropriately sized overcurrent device. It is always recommended to consult with a qualified electrical engineer or inspector to ensure full compliance with the National Electrical Code and any local amendments.